Welcome to module 20. In this module, we will look at the thermodynamic life cycle analysis. So far we have seen the analysis based on energy, and we have learnt about the basics of second law of thermodynamics to calculate exergy for different material streams. In this module, we will go through the exergy analysis, which we call as ICEC or industrial cumulative exergy consumption, and then emergy analysis, which we call as ecological cumulative exergy consumption. So, to begin with, I will give a short history of adoption of exergy in the sustainability field. In 1971, there was this economist, Jost, who recognized that resource quality is even more important than just the availability of resource, because to make valuable product, we are interested in obtaining high quality resources. And he said that based on the second law, economy works by converting high quality resources into lower quality, which occurs by increasing entropy. So, there is, of course, we look at final product and it is of high quality, but there has always been some entropy generated. So, you have taken lot of high quality resources and converted into product which is also high quality, but along with that there is always some kind of waste generation which increases entropy, and that is converting it into low quality waste generation. Then in 1973, Livermore National Laboratory, which is in Berkeley, appointed a joint committee on atomic energy, and they introduced the word useful energy for analysis of power sector and transportation sector. So, they definitely realized that not all energy that is there in the fuel is capable of doing useful work, which is what we are interested in for producing useful output. Hence, they introduced that in power sector and even transportation sector, we should be more concerned about the available energy, which is the actual useful work that can be derived from various resources that are available. Hence, they proposed the use of available energy, which is nothing but the exergy, for analysis of sustainability of these systems. Then in 1974, there was a paper that got published from efficient use of energy, a physics perspective, and it explicitly defined availability or exergy in case of various activities and processes to show how exergy needs to be calculated for various processes and also resources that can be used as a metric to understand what is the useful energy that is available for all of us to conduct the production processes that we are aiming at. Then in 1975, there was a report from American Physical Society, and they found that the current economy was really inefficient in the use of available resources, and about 97% of exergy inputs were being wasted, which means that it gave into insights into how we can improve the economy further, which means improving the processes so that you use the available exergy in a much stronger way to move the system towards a better sustainable outcome. So, from these reports and these developments, there was this movement, or there was this understanding that exergy analysis will be really important in improving the processes towards meeting the sustainable development goals. Let us look at exergy as metric for analysis. So, then what happened is that we start looking at exergy as a metric of resource flow and resource reserves. And the way we define exergy, and we have seen how we define exergy as with a reference frame, it is in more general term, it is seen as the work done to maintain or form the resource in the form it is available. So, if there is a resource that we are making, then we are providing some available or useful work done to make that product, and that is the exergy for that product. So, in a sense, exergy represents quality of resources. The more amount of work you need to do to make a product, it has higher exergy input or higher exergy required to do that production. So, that is the main point, that resources that have high exergy even in a smaller quantity then will have higher impact. So, you may be using, let us say, even a minute amount of critical materials like cobalt and nickel in a highly processed form, which are inputs to the renewable energy system or even to our computer systems. Even though they are used in a minute quantity, they have a higher impact on thermodynamically, because we need to do more work to get that product in higher purity form. Similarly, materials that do not have energy content, which do not have fuel value, they can get ignored in the energy analysis, but exergy captures the material contribution to material potential energy impact or potential thermodynamic impact, because exergy is now telling us how much work is required to actually support the production of that material. And therefore, lot of economists have turned to exergy to capture the resource quality and depletion, and there is of course lot of engineers who are using exergy to improve their production processes or processes to move towards better thermodynamic efficiency. In another way, exergy is also a measure of waste residuals and potential for harm. So, let us say you have a lot of exergy in terms of heat, waste heat that is going to the environment and that is being wasted to the environment. What happens to this exergy? So far we have seen that we do not care about waste heat, but when it goes to the environment, there is always some effect on the ecological systems, which also is now known as thermal pollution. So, when we are wasting exergy in terms of waste heat or any other waste material, it is going to the ecosystems, and because it still has capability to do some work, it actually changes the form of the stability of the ecosystems in some way. Similarly, some exergy is lost as chemically or reactive materials. So, for example, if you have one example is the emissions of N2O and NOx. When they are chemical species which still have some exergy and they are not in the chemical equilibrium, as we talked about the calculation of exergy of compounds. When they are released to the environment, they undergo several reactions and they cause harm to the environment in certain ways. So, when we are quantifying the exergy of the waste that is going to the environment, it also has impact on the environment in certain ways. So, when this exergy is being lost, it does have an impact environmentally in a negative sense if we consider what happens to those pollutant at the end of their life. So, this example I already quoted. When we have some exergy that is being lost as low quality heat, it is being thought that it does not cause any impact, but there has been reported incidents of gradual increase of the freshwater temperature, because you are kind of dumping the waste heat into the freshwater system, and that is known as thermal pollution. And lot of the freshwater fish species and the environmental species are very sensitive to this temperature change. So, in a sense, this low quality heat, even though it is not very visible to us in terms of the pollution, that exergy lost has an impact on the ecological systems and hence on life in the long term. So, what do we do in the exergy analysis system? So, now we know that exergy is an important metric. How do we formulate the analysis using this metric? So, it is very straightforward, similar to the life cycle resource consumption or life cycle energy consumption. We define what we call as cumulative exergy consumption or CYB. So, if we go back to our figure of the network of resource flows. So, we have the industrial processes which are making product Y and it is going into the economy. And of course, the industrial processes require different resources. So, for example, they need some product from the economy itself, they have the natural non-renewable resources, renewable resources, and similarly we have other non-renewable resources going to the economy and the ecosystems, and also we have the waste that is going to the ecosystems. So, when we talk about cumulative exergy consumption, we talk in terms of the total exergy consumption of all the natural resources consumed directly and indirectly in the life cycle. And we also want to say that along with the natural resources, we also add the economic resources. So, any input that is being transformed as well for input to your industrial processes in supporting the production of the required product is what we call as the cumulative exergy consumption. So, when you take a life cycle view, you can draw your network algebra, you can take the whole process network algebra or the input output network algebra and calculate how much exergy of all the input streams that are going into that system, and that is the total exergy consumption for the production of that system. Next, we define a matrix that takes into account the efficiency. So, here we define the matrix called cumulative degree of perfection. So, cumulative degree of perfection is very simply defined as the exergy value of product. So, let us say we are making the product Y divided by the cumulative exergy consumption, which is all the exergy consumption in all the inputs that are given to that product for its formation. So, what it does is that it represents the consumption of exergy for supporting the production of that useful product. So, in that sense your CDP is this very similar to the thermodynamic efficiency. So, if you remember in thermodynamic efficiency, we had the energy value or the thermal value of the product divided by the total energy input. So, here it is the same. Instead, we are using the exergy, and now you can see that we can calculate CDP even for products which do not have any heat value, because in that case now we can use the exergy that is used for making of that product as the exergy value of the product that can be calculated using the thermodynamic references. In terms of the C, which is the cumulative exergy consumption, it can be the exergy of natural resource inputs from nature or exergy of inputs that pass through intermediate processing steps. So, when I say that there are the exergy of inputs that pass through intermediate processing steps, that mean all the products that are being made in the economy, that also requires some exergy. So, then you will calculate the total exergy of value of that product as well, and that is what is being input to your final product formation. So, this can involve calculation of total life cycle exergy consumption for all the inputs, upstream inputs as well. So, you see we can keep on expanding the network, and all you need to do is replace the metrics of resource and your energy with the metric of exergy, and based on the last module you can calculate the exergy of various streams, mixtures and all of those compounds using the different formulae that we looked in the last module, where you have the either the exergy of the pure stream or the exergy of the mixture composition. It could be the exergy, physical exergy, and just the temperature gradient with temperature and pressure gradient both. So, you would really need to look into the inputs and outputs specifically with the chemical and physical composition and calculate that exergy. So, yes, it becomes a little involved to do this calculation. However, lot of the exergy values for standard products are already available in the literature by Zargat and other researchers. So, once you start doing that exergy analysis, you would be readily looking into the literature to get that exergy value. So, let us look at a quick example for the CDP calculation for a product. In this, we have a coal extraction process that produces 100 kg of coal product. So, we have a raw coal that is being extracted, and your feedstock coal is 120 kg with exergy content of 1.8 kilowatt per kg. So, you are saying in this process what is happening, we have a raw coal, we extract it, we process it to refine so that it becomes useful as a fuel coal, and the fuel coal exergy is 2 kilowatt per kg. During this extraction process, you also are giving some fuel oil to run the machineries, and that requires about total of 25 kilowatt of exergy into converting. So, here you need to calculate the CDP for the coal. So, let us take 30 seconds and use the formula for CDP to do this calculation. So, let us look at the solution. So, we defined our CDP as total exergy of the product which is being made in the process divided by the total exergy input in the process. Okay. So, these are straightforward formula, and if you have confusion you can always map it to the efficiency formula that we looked earlier. So, for any of these problems, it is much recommended that we make a input output kind of diagram or a process. If you have multiple process, then you make a process flow diagram. So, here our input output is coal, which is the refined coal, refined in the sense cleaned coal. So, we have coal and you are making 100 kg of that coal and your inputs to the process. So, this is the coal extraction process. So, the input of your process is we have 120 kg of raw coal, which is the feedstock, and we have fuel oil input, and we are not given the total amount, but we are giving the total value of this input is 25 kilowatt in terms of exergy. So, for calculating, we will calculate the total exergy of product. We have 100 kg of product and the exergy of processed coal is 2 kilowatt per kg. So, that is and our total exergy of process is total exergy input to the process. This is about 120 into 1.8 kilowatt per kg multiplied by 120 kg and plus 25 kilowatt. So, this will become about this is 200 in the numerator, which is kilowatt, and the denominator is about 241. So, your CDP comes out to be about 0.82, which means that this process is about 82% efficient in converting the exergy to useful product, which is your processed coal, that is input to other products. So, this way when you are calculating, you can calculate the CDP or the efficiency of all the processes, and then you can compare in between processes to know which process is more efficient in terms of exergetic utilization to make the final product. So, imagine you are making let us say 2 plastic bottles and you have multiple processes, then you can calculate the CDP for that network and you can compare the CDP that will tell you which of these life cycle network is more efficient for you to make that final product, and that is what you should use. We can also look at different parts of the life cycle stages and decide where the exergetic losses are maximum, and there you can invest into improving that process. Of course, when you are thinking of improving the process, there is a lot more engineering analysis that needs to be done in terms of where exactly or what mechanism is behind that exergy loss, whether it is the fluid flow or whether it is a mass flow or anything else, and that is how you would go about improving the process. However, at the life cycle stage, it is much straightforward that we draw all the process flow diagram, we get the total exergy of the product and then we divide by the total exergy input, and that gives us an idea of which life cycle of product is more favorable in exergetic terms. So, that is all in the exergy. Let us move on to emergy. So, this might be a very new term but it has been around for a long time. So, emergy comes from ecological literature. The idea that when we are making any resources or any products in the economy, we are actually doing work. So, any technical process that we are thinking of is about converting resources into some product, and for that we are doing work by giving input. Similarly, whatever we are extracting from the natural system is not coming free. So far, the whole challenge with sustainability is that we have been taking the nature as for granted. We think that nature is just providing resources and we can keep extracting it. But now we know that that is not the case. There is of course the challenge of resource availability. There is also the challenge of how nature is processing waste resources that we are dumping into the nature. So, now to expand, because we want to include nature in the analysis, so far our system boundary has only included the technical system. So, if you want to expand and also preserve nature as you are making products, you would need to also consider that. So, emergy is the thermodynamic way of including nature in our analysis, and here the idea is that the resources that are available from nature are actually energy transformation, where ecological systems are doing the work to provide resources. So, think about photosynthesis. Photosynthesis is nothing, it is more like a reactor. It is a reactor that absorbs CO2 and it is making biomass out of that photon energy or the solar energy that is available by numerous very complex chain of reactions. So, if anyone is interested, you can look into the biology and mechanism of photosynthesis, and it is something very complex series of chemical reaction that takes into the photon, and the cellular plant cells are converting that energy through series into and CO2 into series of this biomass. So, that means that every product that we are taking, whether it is coal, whether it is biomass or whether it is water, it is some part of work done by the natural system, and nature is actually even more complex, much more complex than what we have created in our technical systems. And for that example, if you look at the human body or the gene cellular networks, those have an intricate chain of reactions and intricate signaling pathways that go into that. So, if we really want to capture the role of ecological systems in supporting our need, because if we do not do that, then we are discounting how much more work has been done to provide us the resources. So, in that case, we will need to expand the system boundary to include the ecosystems, and for that what we use the metric is what we call as emergy. This method has been developed by system ecologist Howard T. Odum was an American ecologist who developed this whole idea of calculating the emergy, and the method is developed based on understanding the role and transformation of energy in the ecological systems by drawing the ecological network diagrams. So, the idea is that so far when we are doing exergy analysis or energy analysis, we mostly have industrial processes and we calculate how much, and it can have of course several boxes, which is several processes, and we are calculating what is the product output and what is the energy or the exergy input. But all the natural resources that we are taking, we do not account for what happens upstream in the nature for providing that resources. So, that is where we expand the system boundary, and now we are also looking at the ecological processes, and the ecological processes are taking some kind of ecological inputs. It could be the waste that we are providing, it could be just the energy that the nature has, and any other input that is available in the geological system, and that converts it into the natural resources, whether it be the ore that we are using, whether it is the oil that we are using, coal, it can be biomass, it can be fresh water, and all of that, and calculate the total energy input that is required. So, most of the thermodynamic analysis for natural processes is available from lot of the geology, ecology, or even the atmospheric scientists, because they understand the earth cycle or biogeochemical cycles that is providing that resources, and all of these cycles actually do some work to provide that resource. So, one of the challenges of sustainability is accounting for these ecological systems, because these are very complex and also very uncertain and very stochastic in their nature. So, how is emergy defined? It is mostly defined in terms of solar energy. Eventually, everything that is happening on earth is driving by the solar energy, that is the ultimate energy input to the earth systems. So, the way emergy is defined, it is the total available solar energy that is used up directly, indirectly to make a product. In this case, we include all systems including industrial and ecological systems together to quantify the total solar energy, and we call this energy as emergy instead of energy, and that might be just a way of the ecologists to highlight that this is not our typical energy calculation, but it goes beyond our technical energy calculation, and that is why the word emergy is used. In simple terms, we can also call it ecological cumulative exergy consumption, because we are interested in the exergy consumption, but it involves the ecological process. The unit for this is solar equivalent joules, because remember we are talking about the ultimate energy input to the whole system, which is in form of solar energy. So, let us look at the word transformative. Once we define the solar equivalent energy joule, then we calculate something called transformative, which is defined as solar equivalent joule per unit of joule, or it can also be solar equivalent joule per kg. Sometimes the units can be different based on what you are calculating. But solar equivalent joule is defined as total energy input divided by the exergy output of the product. So, now here you see it is again the efficiency kind of metric, but here now we are talking about the ecological efficiency in making that product. So, let us look at this example where we have the sun which is giving their input to the plants are converting it into coal, because coal is nothing but fossilized plants for millions of years. And then coal is then converted into electricity, and then electricity is input to the product. So, in this whole life cycle network of making that product, now we have expanded the, so we would generally take coal as the natural resources, but now we have expanded the system to include the plants that were used million of years ago to make that coal, and that the plants utilize the solar energy to make that coal. So, now here the solar equivalent energy joule is not changing, because when 10 to the power 6 solar equivalent joule was input to the plants, the same amount of energy got transferred into all the processes downstream. So, you can see that the 10 to the power 6, the energy is the same at each step, because this is what happened at the beginning of formation of the coal. So, there was 10 to the power 6 solar equivalent joule that the plants utilized, and that was converted, and then it became a past. So, in a sense your energy is actually also crossing across the temporal boundary of resource availability to calculate how much was it provided at the time the resource was actually being formed, what was the work done at that time. In a sense, when we do the energy analysis, we are doing same, because most of the time is current, but here we are talking about long term investment of work to make that product. Then exergy of course keeps on changing. So, you can see the exergy of course is the highest quality is 10 to the power 6, but then the exergy keeps on reducing, because we are transforming it into lower quality product that has lower and lower amount of exergy available to do work. And then the transformity is defined at solar equivalent joule per joule. So, if you divide 10 to the power 6 by 10 to the power 4, your transformity of plants is 10 to the power 2, and you can see that your transformity has increased, because now you have same amount of solar equivalent joule, but you are able to only provide a lower quality exergy resource from that input that was done originally from the solar. So, this is how we calculate transformity, is by looking at how much was the total solar equivalent joule input to the process all the way in the formation of that product, and then we divide the exergy of the product or total solar energy joule with the exergy of the product to calculate the transformity. So, it is a simple definition, but in a sense transformity is a metric of resource quality, in the sense that how much work was done to make that small amount of product. So, in this case of course, your product is of high quality since it has high transformity, because you are doing a lot of work to make small amount of product. So, we say that oh, this is a very valuable resource, because we have to, if we have to make the same amount of product again, we will need a lot more energy, while plants are a lower quality product, because you only need to do 10 to the power 2 amount of work. So, if you have to make the same amount of plant as compared to product, you need a lower amount of solar equivalent joule. So, that is the comparison, that higher transformity means that the nature has done a lot more work to provide the same amount of product. So, when we talk about calculation of transformity or the global energy inputs, the total energy to the ecosystems, we have three. We consider what are the inputs from the earth processes like solar, tidal and crustal. So, solar of course is the solar energy, tidal is associated with hydrological systems, and then the crustal is the deep mantle. So, you all must have heard about the geothermal energy being used now, that is the part of the crustal energy as well. So, now you are talking about all the energy. So, in each of the case of course, for solar we can calculate the solar transformity for all type of energy. So, you can see that for the solar energy it is the transformity is 1, but for crustal heat sources and total energy observed, we have about 1.20 into 10 to the power 4, and the power we can say per year is about 8.06 in terms of crustal heat sources. So, this is basically calculating how much is the total energy input to the geobiosphere, and you based on the time it was calculated, you have 10 to the power 24 solar equivalent joule per year, which means that the power that we are getting from solar system is about 3.93, and from the crustal heat sources it is about 8.06. So, let us look at a simple example for transformative calculation in terms of coal. So, here let us say we are producing coal, or the earth system or the ecological systems are making coal. So, we have we consider the processes. So, what geological time scale we produces coal? There are sedimentary cycles that turns the soil, and then the plants go deep into the fossil layers. Then there is rock formation and erosion, etc. So, if you calculate the exergy of the coal, you can calculate it based on its chemical composition and all from the reference state, from the method we have learned earlier, into looking at the reference state and whatever the chemical composition and what form of the chemical composition is that. So, you can calculate the exergy that. Based on the quality of coal, because the chemical composition will be different, your exergy will be different. So, let us assume that for this coal that we are considering here, the exergy of the coal is 29,302 joule per gram. Your global sedimentary cycle flux that is responsible for formation of coal is about 9.3 10 to the power 15 grams per year. That is how much sediments are being turned about in the earth system or the soil processes across the globe. So, the transformative will be total solar and equivalent joule influx in an year, which is about 15.83 10 to the power 24 solar equivalent per joule per year. So, that is from the previous calculations. And now we know that the sedimentary cycle is this much gram per year, and we know that the exergy of the coal is 29,000, which means that if we have to think how much joule per year is being formed in terms of coal exergy, that is about 29,000 multiplied by whatever the sedimentary flux is happening. So, this is the amount of joule per year that is being converted into coal, or the availability of the coal per year, and the total solar equivalent joule input to the whole earth system is about 1523 10 to the power 4. So, I can explain it in the sense that if you consider this earth as a process that is giving coal, and it is actually taking the solar equivalent joule or the solar energy. So, and these are the earth processes. So, what we are calculating is we are thinking of this earth as a process that is giving coal as a product. So, now we need to calculate how much is the exergy of the coal for joule per year every year, and how much is the solar equivalent joule per year. So, that we know from the calculations from the ecologists that it is 15 10 to the power 4. For the earth process, your sedimentary cycle is turning about 9.36 10 to the power 15 gram per year, and we can consider that is amount of coal that is being formed, because that is being fossilized, and then the product that is being formed has this much exergy joule per gram. So, you calculate the total exergy of the product by multiplying the mass, which is the joule per gram is the exergy, and gram per year is the formation of that product. So, you get joule per year, and that is in the denominator. So, from that we get the exergy of the coal that is being formed of this quality is about transformative of the coal that is being formed of this quality is 5.8 10 to the power 4 solar equivalent joule per joule. So, that is how you can calculate the transformative of lot of renewable and non-renewable resources that have been formed by using the earth processes. So, here is an example of all the transformative that has been calculated. So, for sun, of course, it is 1. Wind energy is also caused by the pressure and the temperature gradient. So, the solar equivalent joule for this is 1.5 10 to the power 3. Similarly, rain is caused by lot of temperature gradient and the earth processes. So, you have the transformative for each of these systems. You can see some of the non-renewables, and you can see that coal has a really high solar equivalent joule per gram, it's given in terms of gram, but it has a really high transformative as compared to the crude oil and soil, because soil takes lesser time for formation, or the lesser time for the turnover, and electricity and pollinators have a really high equivalent joule. So, we will talk about pollinators as doing some work in the ecological system, and that is when we get to the ecosystem services module, we will talk a little bit more about pollination ecosystem service. So, in short, we can do three kind of thermodynamic metric calculation. One is direct exergy calculation. So, whenever you have the total energy input and the energy output as a valuable product. Then we have the ICEC, which we call as industrial cumulative exergy consumption, which is the total amount of exergy input in formation of that product. And then we have the ecological cumulative exergy consumption, which is the ECEC, and for that you need to multiply each mass input with the transformity, which will be always, which have been previously calculated for the resources. So, you can do all these calculations and then calculate different metric like efficiency. You can calculate the energy return of investment, you can calculate the cumulative degree of perfection, which is kind of the efficiency metric, and for the calculation of ECEC, we just need to know how much is the total exergy, ecological exergy consumed in that particular system. So, let us do a short example quickly. Here we have a process that is making a reinforced concrete. So, reinforced concrete is where you have combined the concrete with steel or iron to actually reinforce concrete for use in the construction. So, you might have seen lot of pillars that have concrete and they have steel rods or the iron rods that are embedded into it to improve the strength of the concrete for use in the construction pillars. So, this is what that process is, where we have iron and concrete is being mixed, and for mixing of that process you might be using some machine that takes about fuel oil. So, that reinforced concrete processing, maybe you have seen the mixing instruments, and that instrument is taking energy. So, that is the fuel value, and it is giving you reinforced concrete of about 15 kg. So, we are not losing any mass here, we are making equal mass after combining of all the product. So, here what you need to do is you need to calculate the transformity that will tell how much is the solar equivalent joule per joule for this concrete, and these are all the inputs to the process with their equivalent transformity. So, let us take 30 seconds and calculate the transformity for this reinforced concrete product. All right, let us look at the solution for the transformity calculation. So, as we know, the transformity is simply defined as m by b, where your m is the total energy input to the product, and b is the total exergy of the product. You can also do it per unit mass, but mostly it is defined as total exergy of product, because we are concerned about the useful available exergy. So, now for total energy input, it is straightforward because you know the inputs to the process. So, you can calculate the ecological cumulative exergy consumption by multiplying these mass by the transformity, which is telling how much ecological cumulative exergy consumption has happened per unit kg. So, here we have 5 multiplied by 2.50 into 10 to the power 9. The other input is concrete. So, our concrete has 2.59 into 10 to the power 9 multiplied by 10, and then the fuel oil is about 1.0 into 10 to the power 4 multiplied by 5. Okay. And then the total exergy of the reinforced concrete is 200 joule per kg. So, you have 200 joule per kg multiplied by the 15 kg of the product. So, when you calculate that value, your transformity will come out to be 1.280 into 10 to the power 7 solar equivalent joule per joule. So, you can see that you have the quality of the product. So, now if this reinforced concrete is an input to another process, this is the transformity of that product that you will use to calculate the ecological cumulative exergy consumption for the other product. So, we might be, let us say we might be making a pavement and we will be using the reinforced concrete or we will be making a building, we can make a reinforced concrete input, we might have an electricity input to that, and we might have, let us say, a pillar that is being made. So, now if you have to calculate the transformity of the pillar, you will use the you will use the transformity of the reinforced concrete, how much reinforced concrete is being used, how much electricity is being used. You calculate the total ecological cumulative exergy consumption by looking at the transformity numbers, and then you can calculate the transformity for the pillar. So, this is how you can keep on doing for each of the life cycle stage for which you want to calculate the ecological cumulative exergy consumption, or emergy. So, emergy is a term that confuses a lot of people, but it is not a made up term. It is actually the ecological cumulative exergy consumption that it is being used in the whole system. So, what it does is that it gives us an expansion of including also the work done by ecological systems in providing that resources. So, it is in the true sense the thermodynamic sustainability of the system, because now you are not missing any useful contribution in making your product. So, in short, in summary, the thermodynamic based LCA is a really good metric, or is a really good method to understand how energetically favorable your process or product is on a life cycle scale. So, to do that, we do start with identifying the scope and system boundary like we do in all LCA systems, and then we can calculate the resource consumption energy inputs for the defined functional unit. For all the resources, because lot of time these resources do not have energy values, so you might be missing the contribution of these resources in terms of thermodynamics. So, that is why we combine it with exergy and emergy values. If you just want to know the exergy value, we can follow all the approaches in the previous modules to calculate the exergy of that stream based on the physical and the chemical properties given to you and choosing a valid reference state. For emergy, you would want to know in terms of the transformities. So, transformities of lot of non-renewable and renewable resources based on the earth system processes have already been calculated. For calculation of the transformity of a product, you would need to know the transformity of each of the inputs and then use the metric of transformity as total emergy input divided by the total exergy of your product or mass. If let us say nowadays we are also talking about improving our systems by introducing recycling technologies or creating circular economy. So, if you are expanding further and using abatement technology, or you are using cradle to cradle approach that we call, instead of just leaving at the end of life, we are also recycling. What you can do is, for all the additional processes, you can do the exergy quantification that is required, and that will give you the true thermodynamic sustainability of actually recycling the product as well. And unless we include that, we cannot say that by just recycling we are making our system better, because we might be using a lot more energy and it might not be that beneficial. So, even picking in between two recycling technologies, you can do a thermodynamic analysis using exergy metrics or emergy metrics and understand the true value of introducing such abatement technologies in the economy. So, let us look at last some of the implications of second law for sustainability. Our second law says that due to inefficiencies in the conversion of heat to work or other useful output, there will always be more energy required to perform same work. And as the available energy decreases in the economy, it will be more difficult to achieve the same output. For example, if the temperature difference decreases, less work can be done. As the concentration of material decreases, we saw that the energy return of investment is becoming higher or becoming lower for the same amount of extraction of oil, and similarly the exergetic efficiency will also decrease. So, it can be a very important metric to understand that how sustainable we are in terms of material extraction and utilization, in terms of the quality of resources that are available. Hence, when we are comparing systems from a thermodynamic perspective is very important, because which system on life cycle stage is better in terms of energy conversion that is available to us for performing useful work is a very important metric, and it should be used along with all of the life cycle impact assessment that we have learned in terms of the impact on the ecological systems. With that, thank you for coming to this module. In the next module, we will start looking at some other metrics like footprint metrics for evaluation of sustainability of different systems, and then we will move towards the ecological systems or ecosystem services.